Yes. Now what shall we do?
So
I mean, we have a little bit, some idea about what strain gauge is, how to resolve X, Y, and so on.
yeah, but I mean, if you look at this strain gauge sensor, it seems like it's quite easy to fabricate, right?
Yeah.
Design and also place on the target.
Correct.
So it's probably one of the more useful.
Actually, it is widely used.
Services.
Various applications it is used. And even to, let's say, measure some mass. When you buy something from a shop, they keep it on thing, it shows a display.
And that's strain gauge.
It could be strain. Yeah, it could be.
I think it's common maybe. Strain gauge as well. What about our
when you check our
weight?
Our weight, that with a nice display it comes.
Exactly.
That's also, I think, they call it as a load cell. We see that soon. But primarily it is a strain gauge, right? On a suitable, pasted on a suitable structure. So it could be just like a cantilever.
Okay.
So cantilever means, let's say, we all have the measuring scale. I mean, if you keep it on a table, press one side, the other end, if it is extends outside, that's a cantilever. You're correct. Yeah. So basically, if you press the free end, it will bend. I can draw here. So let's say I have a end which is fixed, and from there, let's say I have a structure like that. Okay. So if I apply some force here, or if I put some mass there, basically this guy will bend a bit. I'll draw maybe a it will not bend this much, sorry.
Depending on the
correct
mass.
Yeah. Could be like this.
So what you're saying is this could be maybe a method to measure mass.
Yeah, is it? Yeah, because see, this end is fixed. You are applying something. This cantilever material, let's say it's in the elastic region.
Okay.
So you apply a force, it bends. And then when it bends, basically, there is some stress experienced by this material, right?
Right, it is fixed.
Correct. Actually, I don't know whether it is obvious. I mean, which region will have more stress? I mean, whether this region or center region or the tip region. Yeah. So when someone looks at it, a lot of strain in this area. That's what the quick feeling they may have.
Yeah, because visually it seems like
looks like that. Looks like that. But the scale experiment, maybe you can try at home. When it's a plastic scale, press one side, which is on the table, and bend the other side as much as possible. See where it breaks.
Right, it is fixed.
Yeah. So it breaks at the place where it is fixed.
Right.
Correct? Not the other ends.
The other end is free to move.
Yes. Yeah. So the stress is maximum in this region.
Right. I mean, that's kind of understandable if someone's holding you and not letting you go.
Yeah.
You probably have more stress than
Correct. Yeah. So the scale experiment actually shows you where it breaks. Yeah. Because there it went beyond, I went into the plastic region, yield strength. So beyond the yield strength is ultimate strength and the finish.
Okay.
Yeah. So that means I can maybe look at the strain in this region. That will be a function of the either force or mass that you have kept. All those will be function of that.
That's interesting. So that's another example of using strain gauge
to measure
mass.
In this case. You can do more about it, but mass is one of the parameters that you can measure.
Right. So rather than
Yeah. So now maybe if I draw a top view, let's say a beam, something like this. Let's say it's a top view. So it will be firmly fitted on one side. And then I will introduce strain gauge. Like this. So basically we are applying the force or mass here, it goes down. So there is a bend here or an expansion there, which is sensed by the strain gauge, which is proportional to the mass. Yeah. As simple as that. So it's a nice way of making. It's a nice one. Now, I have a question. See, we introduced, maybe I'll, this is top view. This is a side view, right? I'll draw the top view again. Not very good, but yeah. So when it bends in this direction, we said there will be an expansion in this region.
This is a side view you're talking about.
Yeah, side view. Yeah. Yes, correct. So we have put the strain gauge there. Nice. What will happen to this region?
And that will also bend.
It will also bend. So if this is expanding, in this region, if it is expanding, will this also get expanded or it gets compressed, right? So there will be a compression. So now if I put one strain gauge at the bottom also, right? So I can put one strain gauge here and another strain gauge at the bottom. Let's say SG1 and SG2. Yes. When SG1 undergoes expansion, SG2 will undergo contraction. And vice versa. I mean, suppose if the force is from the bottom.
Yeah. Then the other way around.
Yeah. So this may be a way to get, you were mentioning about sensitivity once. I can get maybe more sensitive output. In the sense, here let's say it's, we said R0 into 1 plus or minus x, sorry, kx. Here then it will be R0 into 1 minus or plus. Yes, kx.
Correct. So this ratio of stress to strain for a given mass, is it normally the same? What's that relationship like? So what I'm saying is, let's see here.
So that's what we discussed earlier, something called gauge factor.
So even for the cantilever?
Yeah, same applies for the cantilever. Yeah. So if it's in the elastic region, so when we did the stress strain curve, what you're seeing is it goes like this and then after some time it breaks. Yeah. I mean elastic and then finally. So if you are in this elastic region, then for a given stress, it gives the same strain or it is repeatable. That's what kind of your question, I guess. Yeah.
So then there's also some sensitivity there.
Yes.
You can derive from this.
Yeah. So basically for these two resistors, if I can maybe take a difference, then I will get double the value. Yes. Correct. Yes. So these are, I mean, some ways to, what shall we say, realize some practical applications and even to get more sensitivity and so on.
So these cantilever structures you're talking about, I mean, how large are they? Are they large? Are they big? Or
it depends on the application. See, there may be cantilevers with a couple of millimeter length. There may be cantilevers with meters long. I mean, not for measurement purpose, right. But I've seen, the structures where, some of the buildings when you enter, you will see that there is a structure standing with no support. Sometimes, right. Porches and etc.
Right.
So that's also on a cantilever.
Something. And also the diving boards, I think.
Correct. Exactly. That's also, so cantilevers are widely used in various applications. Right. Here we are using it for measurement.
Sure. Very nice.
Yeah.
Now, another thing is, so these cantilevers, now you're applying a weight, right? But then if you give it a force and let go, it will somehow vibrate.
Yes. So it will oscillate. Yeah. So the same scale experiment. I mean, if you press one side, whatever the free end, if you give a impulse, right, it will actually oscillate at its resonant frequency.
Right.
Correct. Yeah. So that is also, I mean, people use that to, what shall we say, even to measure mass in certain applications. Because that resonant frequency is also a function of that length of dimensions of that cantilever and the mass in this region.
Oh, and you have a fixed mass there.
Suppose let's say you wanted to measure some parameter, some environmental parameter, for example. There is some deposition happening.
Okay.
Due to the particles in the
measure the concentration.
Yeah. So that changes a mass at the tip a bit.
Right.
So then the resonant frequency will change.
Okay. So it's oscillating.
Yeah.
Depending on how much of these particles are on it, it will change.
Correct. Okay. Again, the scale experiment they can try. Try for a different length of the free end length can be adjusted. I mean, I can push the scale more into the table. Plus, so if it's shorter, the frequency will be higher. Right. Right. Maybe we'll see that in detail later. Yeah. This is something connected where while if you are installing strain gauge on a given structure, this doesn't apply. I mean, what I've drawn earlier, you have a cantilever and then you are pasting a cantilever on that.
Yes.
Right. These diagrams, I mean, sometimes when I said it's a millimeter size, etc., then the cantilever and the strain gauge may be fabricated using some MEMS technology.
Okay.
Right. There, as you can see here, cantilever is made and then the strain gauge material is deposited on that.
On top.
Right. So it could be doped resistor. Right. Various ways to realize.
Right.
Bit different from the standard strain gauge insulation that we discussed earlier.
Right.
Because these are fabricated together.
Yeah.
Some of the ineffective designs, etc., shown here. I mean, suppose if you say, your cantilever is this, but if the strain gauge is so big, then
might not.
Yeah, it's not the best. Yeah. In fact, it may share some load, which we don't want. And if somebody does this kind of design, the cantilever will break. Right. So some ineffective designs, just to, it could be deposited or doped. Deposited means it's on top of that, or it could be topped. But these are, what shall we say, mostly applicable for MEMS structures. Right.
Due to the scale of.
Yeah. MEMS, microelectromechanical systems. Yeah. That our students might not have, may not be familiar with. Probably in a future course, they may see more about that. Right. Basically, the dimensions are quite small, so you will need specific fabrication processes to realize that. While structure like this doesn't. It's quite large, and there the fabrication mechanisms are different.
So, that makes sense because you talked about measuring the concentration of, let's say, some particle.
Yeah.
The particles are in the millimeter or
correct.
Small
micrometer size.
Micrometer size, then you need something smaller.
Yes.
Right?
Yes.
That's
otherwise this structure
relatively small.
Correct. This structure, it doesn't matter.
You probably even break it.
Yes.
If it's too small.
While if it's very small, for that relatively it is large.
Exactly.
So that way you can make it more sensitive to
correct
what you want to measure.
Other one too, if you have such a big strain gauge, plus little particles.
Correct.
Even for large structures, we get a very small K.
Correct.
So you can imagine for such small particles be.
Exactly. Exactly. So that is for, this I mentioned for MEM structures, small size. But if you want to measure some, let's say kgs, 2 kg, then you will need different structures. Yes. So this is one of them.
What is that?
So maybe if you look at the figure, see, you have got a structure like this. That's the one carrying the load. In the sense, suppose if I apply force here, this. So maybe you can also see there are some screw holes.
Yes. So the strain gauge.
No. So these are used to fix to a, what shall we say? See, when we have drawn a cantilever, we said this is fixed region. Yes. But now how do you fix it? So most probably what you will need is, this will have to be extended somehow, and then there should be a structure here, and then you put nut and bolt there.
So that's what we're done.
Yeah. So you need that to insert, and my drawing will not be proper, but to tight it to a structure.
Now I'm surprised, Boby, that you did not take this apart, because you always taking things apart, seeing what's inside.
Yeah.
Maybe these are expensive.
It's actually not very expensive. We have here. Maybe next class we can show.
Okay.
Yeah. So these are used to firmly fix to the structure.
So there are multiple cantilevers.
No. This is actually one cantilever, right? This side it is fitted, and then this extends. This is the free end.
Okay.
So in the free end, let's say if you want to measure mass, I can have a some kind of structure, and that can also be tightened to this way
on top of it.
So the basic weighing machine, for 2 kg, etc., that we see in the shop,
right,
is something like this. So where you have a structure where you put the object,
right?
Yeah, and it shows a display.
Display.
Yeah. So this is one end, it is fixed. The other end is free, and at the other end you have that I don't know what to say, tumbler or what.
Oh yeah.
To put your things and measure. Yes. So that also needs to be fixed. That's why other set of holes here.
I see. I see. And what's the one thing at the end, the other end?
The other end, these are the cables.
Okay.
Yeah. So now you see the strain gauge. So maybe this much portion corresponds to this portion. Yes. But it's it's used to fix it. Then the strain gauge, the cantilever comes out. So this region you can see some eye kind of structure. Actually, it's a hole. So the material there is taken away. Or I will draw here. It's not to scale, but let's say, or let me draw it slightly bigger. Let's say it's like this. Now we said we will apply force here, or we'll put the mass there.
Yeah.
Now to have the screws and etc., the structure has to be of some size.
Yes.
Correct?
Yes.
Now if it is of so thick, and if I want to measure, let's say 1 kg, the expansion, contraction, etc., that we see here may not be much, right?
I understand.
right? Now, how will I make it more sensitive?
Take some material out
You take some material out. So,
or amplify the bending.
yes, so they have taken this out. So that's why it is, that's what
The whole
is seen here. Yeah. So that way, now, sorry, the cantilever portion is only this much.
Yes.
Sorry. Okay. I think that undo is not possible. Only this region and bottom this region. So the expansion contraction will be more. And they have introduced strain gauge actually here.
Where you see the most window.
That's what a black color structure is seen. And from there, the wires are coming. Right. The drawing, I made a mess out of it, but I think it's somewhat clear.
No, I think it's very clear. I think,
Yeah.
And what, so do structures like this also have a strain gauge under?
So in this image, they have used only one.
Right.
But I can have here also. That's the correct question.
Because you have taken the material out in a way
Yeah.
that implies that you can probably put strain gauge on top and bottom.
Yes, I can do this way. Right? And since you asked that question, we can also now I'll ask a different question. So far it's correct, right? So let's say this top portion, let's say it undergo expansion.
Mhm.
What will happen to this portion?
You mean the hole?
Below the hole. I mean, there is this region, no?
So it will then compress.
It will compress.
I can put another one there.
Yeah. So you can actually put one there. That will undergo contraction.
Right.
Sorry, the other way. Right. Now, this one we said it will also undergo
Compression.
Yeah. Then what about this region?
You expect.
It will expand.
So, then if you take the top two,
Hmm.
the ratio and the bottom two ratio should be the same according to stress strain curve, correct?
Yes. So this means now I can get 4 strain gauges and 2 of them are in push-pull manner in the sense, let's say RX1 and RX2, they change in a push-pull manner. Yes. Similarly, this RX3 and RX4 will also behave in a push-pull manner. Yes. When I say push-pull, when one increases, the other decreases. Right. So this way, the bridge that we were talking earlier can be modified. See, earlier we had a Wheatstone bridge with one sensing element. Yes. Now I have 4 sensing elements. So all of them can be part of that bridge now.
So 4 or 4 part of it.
Yes. So
And all 4 are changing.
all 4 are changing.
I mean, the reason we had one
Hmm.
is because we wanted to somehow see that small change. And the other ones were fixed.
Correct.
But now, I mean, assuming the change is still small, you're saying we can put 4 and somehow increase.
I'm just thinking we can put 4. So I may not be right, but let's try. So I think that region it is.
It's at the top, huh?
Yeah, something is not right.
Okay. Then have to redraw that from.
Yeah. In that case, maybe I'll make a new page. Yeah, I think this is the bridge that we discussed earlier. And this one was like Rx, sorry, we said Rx, then it was R naught into 1 plus or minus Kx. Now we have 4 of them. So what we said is if 1 is increasing like this, there is another one which decreases. So where shall I keep the decreasing one?
This one is the increasing one.
This is increasing one. Suppose it increases here also, then it may not help. No, correct? Because what we are taking is the difference in voltage.
So in the top left.
So maybe I should keep here. This goes down.
Yes, correct.
So this should be R naught into 1 minus or plus Kx. Okay, then this can be something goes up.
One goes down.
Or
you mean there? What more?
Or did we make a mistake?
So I think that one should be
opposite.
Yeah.
Okay.
Then minus 1.
Yeah. Or maybe it will be easy to think about this bridge, this portion, I think. Then we will get maybe better clarity. If this is increasing, and if this is also increasing, then this voltage will remain same.
Yes.
Correct? Yes. So it has to be decreasing. Yeah. Correct. So it has to be R naught into 1 minus or plus Kx. Now this side, it has to be opposite of what you got. So it has to be something which is decreasing, and this has to be increasing.
I mean, the other way around will also work, but this will give us higher sensitivity.
Correct. Yeah. So this has to be R naught into 1 minus or plus Kx, and R naught into 1 plus or minus Kx. So in this condition, actually the difference in voltage, or V naught, we have to see what it will be. But probably it will be better than what we had earlier.
Yes, I believe so. Because now we have arranged it in a way that somehow
the differences gets added.
Exactly.
Correct. Anyway, if Kx is 0, all these elements have equal value, and hence output will be 0.
Yes.
That's clear. Yes. So maybe we can give some, let's say this is plus minus, let's say this is A and B. So voltage at A will be Vs by R naught into 1 plus or minus Kx plus R naught into 1 minus or plus Kx multiplied by, this is BA.
Correct. Voltage.
Yes. Minus BB, again Vs into R naught into 1 minus or plus kx divided by the same. Same means R naught into 1 plus or minus kx plus R naught into 1 minus or plus kx. So actually, if you look at the denominator, plus or minus kx, minus or plus kx, it will get cancelled. So it will be 2 R naught denominator. Yes. So
R naught is common to both.
correct.
Yeah.
So R naught into 1 plus or minus kx divided by 2 R naught minus R naught into 1 minus or plus kx by again 2 R naught.
Mm-hmm.
This means, as you said, I can cut all these R naughts.
Take the half out.
Yeah. Vs by 2. Should I take out? Anyway, let's see. So this will become 1 plus minus scale 1 and 1. 1 minus and the 1 that will go away. I have plus or minus kx minus
Then
my
same becomes plus or minus.
correct. So we have plus or minus kx minus plus kx. So that means 2 times
kx.
correct. So which is Vs into kx plus or minus.
So yes, it doubled.
Doubled or
We had Vs.
so earlier what I remember is it was some Vs into kx by, so we had 1 plus or minus kx by 2 here, but it was 4, I think.
No, when you after you solved it with the amplifier, it became
With the amplifier. With the amplifier. But probably we need to compare with
before
without amplifier. We can just cross check. We have this here.
Yes.
Yeah, right. So it's Vs by 4 into this one.
4 times.
So it's 4 times because now we have 4 strain gauges. All are aiding. Somehow we have connected in a way that they are aiding. Right? So we understood that one is increasing, other one is decreasing, and this is increasing, this is decreasing, and so on.
And that's only because they're right below each other.
Yes. So that way, this is much more sensitive.
Yes. And somehow linear?
Of course. Of course. So it has come automatically linear. There is no denominator term. Earlier we had a kx by 2.
Kx by 2, yes. 1 plus.
Yeah, 1 plus kx by 2. So this is more sensitive, and there is one more advantage. Now, I'll, let's say, any, material, conductive material also has got, if temperature changes, its resistance will also change.
Okay, yeah. Okay.
Correct?
Yeah.
So we say temperature coefficient of resistance.
Yeah.
So if all these elements, they will be sensitive to temperature. So that means I will have to actually write R naught into 1 plus or minus kx into, I'll use a different color, maybe 1 plus alpha T. Alpha is a temperature coefficient of resistance.
Okay.
R naught into 1 plus alpha T is the standard equation to find out what will be the resistance of the element at
certain
so and so temperature.
Okay. And if you obviously you make the strain gauges from the same material.
Yeah.
So all of them will have the same.
Will have same alpha.
Same alpha.
Temperature coefficient of resistance. Alpha. Okay. So this will also have same alpha, as you said. One plus alpha t into 1 plus alpha t. Suppose the earlier one, where you had 4 elements in the bridge, only one is strain gauge. That alone changes with temperature.
Yes.
Then your output, bridge output, could be due to change in temperature.
True. Assuming that the other 3 resistors are not made from
Made of same material and not exposed to same environment.
Yes.
Let's say the bridge is sitting in the office and sensing element is in the field.
And they have different.
Yes.
So you don't know if the change is due to the stress strain or temperature.
Yeah. Possible. Very much possible.
Yes.
So now in this case, all of them will have this 1 plus alpha t.
Yes.
So now if you look at here, what will happen? All this time will have 1 plus alpha t. So, like R naught got cancelled, this will get cancelled.
So there's no temperature dependence on this outside.
Yes. So the output is insensitive to temperature. Yes. Correct?
Correct. But then this
you are not doing anything. Just
no.
Make the same material. Use all the 4 elements using the same material and expose it to the same environment. When if all of them have all of them see different temperatures, then it will not help. But in this case that we explained, it's on a piece of material. Conductive, for example, aluminum or so, and mostly same temperature will be seen. Experienced by these strain gauges.
I guess a load cell like you showed is harder to fabricate compared to the simple sticker structure you showed before.
Yeah.
Right.
Yeah.
But then the biggest advantages, as you can see, that depending on temperature, and then you get linearity without even
no additional electronics. Yeah. Now, if you want more voltage, of course, you can have an amplifier. This V0 can be amplified, and then if that is required. So now these 4 strain gauges actually brought in so much of benefits.
Yes, but this is for the measurement of mass, correct?
Now I can see this drawing is for measurement of mass.
Okay, but what about your sticker structure? I don't think.
Which structure?
The sticker, like before you had a rod, steel rod, and then you had a sticker. We talked about different orientations.
Here.
Yes. Can we use a similar structure or, multiple strain gauges to get a full Wheatstone bridge? Is that a possibility, or is that one of the limitations of fabricating in such a way?
This we will have to see. 4 sensing elements may be possible, but 4 of
push-pull, right?
Yeah, 4 of them in push-pull is also possible in certain applications. Right. So we will come to that. For example, let's say you are measuring torque.
Okay. Then you have 4 different directions.
Then it is possible.
You can place it.
Yeah.
Okay.
Yeah. So
right.
We will come to that.
Okay.
So it depends on the application, but in general, what we know is this is possible.
Yes.
In the sense, the push-pull arrangement can be obtained, and that has got this benefit. Yes. Yeah, this we discussed.
Mm-hmm.
What is this? I see a proof mass.
Proof mass. You did mention attaching something to the end of a cantilever.
For the sensing push.
Sensing push.
Yeah.
Sensing push.
Correct. Right.
But why?
So if we want, we can have our own mass. Correct.
Yes. If you know
the earlier drawing was just a cantilever like this.
Yes.
But I can have a cantilever whose free end has got some specific mass.
Correct.
Possible. It's only up to us.
Yes.
Right. This is the top view, and this is side view. Right. And the strain gauge is fitted here. I mean, installed here. All these are fine. I'm trying to make out what is this used for. We have talked about mass. We have talked about force.
F equals ma.
F equals ma. Yeah. So that kind of tells us that anyway, this guy can measure the force.
Yes.
And if you are setting the mass here,
A known mass.
then of course, acceleration A can be measured.
This is true.
So if you have a structure where you have a cantilever coming out with a known mass, let's say it is packaged in a way that so maybe let's say we have a something like this, and the cantilever comes out, I mean inside, with the proof mass. And we have the strain gauge here. So this entire unit, I mean, I can just move up or down.
And this will
It need not oscillate. I mean, when I suddenly move this up,
do go up.
yeah,
Come down.
but the mass will try to stay there
Yes.
due to the inertia.
Yes.
And that force is measured. M is known. So the acceleration can be calculated.
So the strain gauge again plays a key role. Right?
Yes. Yes. Yeah. Now, why I have drawn this is, otherwise it may not be obvious, because it has to be in a housing, and that housing experiences this acceleration.
Yes.
And the mass always try to stay there due to inertia.
Yes.
Like in a bus, when they suddenly apply a brake, yeah, we continue, this mass continue to stay there, correct? While bus wants to stop or go fast, depending on accelerate or decelerate.
Yeah, they go this
Yes.
go this way, right? Same thing.
Same thing. So at that time, we may be holding on this thing, and the strain that we have here is, measured in a scientific manner using a strain gauge.
So we can measure acceleration.
It could be an accelerometer also.
Accelerometers are used in so many different
Yes,
applications.
yes,
Right?
yes.
One of the most common sensors.
Yes. This is one way to realize an accelerometer. There are various other ways to realize that we will see later. And if one wants to calculate the displacement, etc., I put the equations here. I mean, force, length, width, thickness, Young's modulus, and so on. Right?
So this also means, looking at the structure and what you explained before, I guess you can make these accelerometers very small.
Yes, it can be small, it can be large. Right, all these are possible depending on the speed that you want to respond and so on.
Right, and also if everything is small,
correct,
you probably don't need a lot of power.
Exactly. Yeah. So this is another nice application.
Strain gauge.
Yeah. And from strain gauge, we have learned strain gauge. We have learned certain applications now. Measuring acceleration or measuring mass, measuring force, cantilever, things like that. All these designs are using cantilevers.
Yes.